Hello everyone. You can cross-check now the solutions of the assignment number 6, which is on the Taylor's and Laurent series. Remember the most important formulas for the Taylor and Laurent series that you should know is only the two formulas are there, known as 1 upon 1 minus r. 1 upon 1 minus r is 1 plus r square plus r cube plus so on. So this is the one formula which is the most important. 99% of the case you require this formula. The other formula is 1 upon 1 plus r, where we have alternate plus and minus sign. 1 minus r plus r square minus r cube plus so on. And the most important thing, both these formulas are applicable only if mod of r is less than 1. So whenever mod of r is less than 1, if mod of r is less than 1, then only these formulas are applicable. That means we can write 1 upon 1 minus r in the series form, provided mod of r is a less than 1. So this is an important condition known as a region of convergence on which we are expanding our series. So everywhere our focus is to write the term 1 upon 1 minus r, where this r, magnitude of r, is a less than 1. So come to our question now. We have to expand this 1 upon z minus 1 into z minus 2 on the different region. So the first case, or before that, so given f of z equal to 1 upon z minus 1 into z minus 2. Step number 1 for Taylor and Laurent series, always we have to separate this linear factor by a partial fraction. So 1 upon a upon z minus 1 plus b upon z minus 2, that is a simple partial fraction that we have. Now to get the value of a, we'll replace z equal to 1 except that factor. So 1 minus 2 is a minus 1. So minus 1 upon z minus 1. So that is the value for a. Now we'll replace z by 2 to get the value of b. So 2 minus 1 is a plus 1. So 1 upon z minus 2. This is the value of a is a minus 1, b is a 1. This is by partial fraction. And let me give this as equation number 1. So this is our f of z. Now our aim is to write this f of z in the uh, powers of z or powers of z minus 8, depending on the region of convergence we are given. So if you see the first bit of the question, is mod z less than 1. We have to expand it on the mod z less than 1. So let me start the first bit here. So a bit is a mod z is less than 1. Remember, in the first term we have 1 upon z minus 1. So either we can take minus 1 common so that we get 1 minus z, or we can take z common so that we get 1 minus 1 upon z. So it depends on which region we are given, that we have to take as a common. Similarly, from the second term, either we can take z common or minus 2 common. But here, as mod z is less than 1, we can observe, first of all, if mod z is a less than 1, mod of z by 2 is also less than 1. Mod of z by 2 is also less than 1. Therefore, by 1, this indicates what should be the common. F of z can be written as, from the first term we just take minus, we'll merge in the denominator, or we take a minus 1 common, so we get 1 upon 1 minus z. And the second term, we are taking that 2 as a common, and we get 1 minus, not 2, minus 2. We take minus 2 as a common. So 1 minus z by 2. Remember, the best part that has happened is it is in the form of now 1 upon 1 minus r, where this mod of r is a less than 1. Same thing, it is 1 upon 1 minus r, that is z by 2. So mod r is a less than 1. So both the places now we can apply that formula, that is 1 upon 1 minus r is 1 plus r square and so on. So the next step, just the standard formula that we seen at the beginning. So 1 upon 1 minus r. So expansion of this first term is 1 plus z square plus z cube and so on. So this is the expansion for the first term. At least 3 non-zero term you should write it. Minus 1 by 2 is a constant as it is, And then we have the expansion of 1 upon 1 minus z by 2 as 1 plus z by 2 plus z square by 4 plus z cube by 9 and so on. But at least three non-zero term I written. Both are in the power of z. Yes, we can simplify. We can collect the terms together. This 1 minus half, that is the first term I am collected here. Constant terms collected. Now let me collect the coefficient of z. 1 minus 1 by 4 of z plus 1 minus 1 by 8 of z square and so on. So the last step we get 1 by 2 plus 3 by 4 z plus 7 by 8 z square and that so on. So whenever we have that mod z is less than 1, for that our f of z can be written in the Taylor series form. Why it is a Taylor series? Because only positive powers of z appeared in the final expansion. So whenever there is at least one negative power of z or z minus a, we say that is a Laurent series. So that about the first bit of the question where we expanded our series in for mod z less than 1. Now we have to expand it for the region between 1 to 2. It is actually the annulus. The first region is actually the circular region inside the circle, inside the circle of radius 1. Second one is the region inside between the two circles of radius 1 and the radius 2. This is the annulus. Okay, so for this we have to find out the Taylor or the Laurent series. So, so if we see here, just a minute. Okay, this is a creating problem now. Okay, wait, take at least 2 3 pages. And now let I shift whatever I done at the beginning on the top of the. So these are the formulas. Just a minute. Huh? I should do that at the beginning only. And the second part. Okay, so that about solution. I'll delete this part. Just 1 minute, just 1 minute only. It's my mistake actually. Okay, that's fine now. That is enough. I think this is enough space now. Okay, a bit we completed. We are moving on the second bit now. 1 to 2. Okay, 1 to 2. So let I do the second part here. B bit that we have is 1 less than mod z less than 2. Remember the first inequality 1 less than mod z gives us 1 by z. 1 by mod z is a less than 1. Similarly, the second inequality because we have two inequalities there, one less than mod z and mod z less than 2. Mod z less than 2 implies that mod z by 2 is less than 1. So these will act like our r now. These will act like our r. So if we see the equation 1 now, by 1, we have f of z as minus 1 upon minus 1 upon that z minus 1 and plus 1 upon z minus 2. This is the equation 1 that we have. So from that equation 1 only, what should be our r now? 1 by z and z by 2. So to get 1 by z from this, obviously we should take z common, and to get here z by 2, we should take minus 2 common. So that indicates what should be the common from the equation, and we get minus 1 upon z into 1 minus 1 by z, and here we take minus 2 as a common, just like a previous previous case. So this minus 2 is a common, and we left with 1 minus z by 2. And now the last step left, we have the expansion. We have the expansion uh, like the previous one only. So it is like 1 upon 1 minus r expansion. So the next step will be this minus 1 by z as it is, and the expansion of 1 upon 1 minus 1 by z is 1 plus 1 by z plus 1 by z square plus 1 by z cube and so on, and minus 1 by 2 minus 1 by 2, it is 1 plus z by 2 plus z square by 4 plus so on. You will observe the previous terms will have the negative powers of z. The first part of the series is the negative power of z, and second part have the positive power of z. So there is no simplification possible. Okay, only you can multiply minus 1 by z inside the bracket and this minus 1 by 2 inside the bracket. That can be a simplification, not more than that. So that about our Laurent series now, because we are getting negative power of z. So that about case 2. The case 2 is we have mod z in between 1 and 2. Third case is a mod z greater than 2. Mod z is a greater than 2. So that about our third case. So case number 3, that is C bit, is mod z greater than 2. So mod z is greater than 2 indicates 2 by z. Mod of 2 by z is less than 1. You will observe mod of 2 by z is less than 1. If mod of 2 by z is less than 1, you will observe mod of 1 by z, you divide both sides by 2. So 1 by z is less than 1 by 2. So less than 1 by 2 means obviously it is less than 1. So which mod we have less than 1? 2 by z is less than 1 and 1 by z is also less than 1. So that can be our r now in the equation 1. So already our f of z is minus 1 upon z minus 1 plus 1 upon z minus 2. We should have 1 by z and 2 by z. So both the terms we should take that z as a common. So if you take z as a common, so 1 upon minus 1 upon z into 1 minus 1 by z plus 1 upon z in bracket 1 minus 2 by z. So that about the replacement. First taken common here. Now we are going to expand this in the powers of r. Our same series, same formula. 1 upon 1 minus r is 1 plus r square and so on. So minus 1 by z from the first term as it is, and the expansion 1 plus 1 by z plus 1 by z square plus so on. And second term 1 by z as it is, and the expansion is 1 plus 2 by z plus 4 by z square plus so on. Okay. Uh, So this will be the expansion there, and now you can take the commons there. Okay, you see both have the negative power of z. You can combine them. First is the minus 1 by z. Next series have plus 1 by z, gets cancel each other, and you get a simplified answer there. So if you collect the similar terms together, minus 1 by z plus 1 by z is a 0. This is minus 1 by z square plus 2 by z square become 1 by z square. Next, minus 1 by z cube plus 4 by z cube become 3 by z cube. At least we should write three non-zero terms. So I will take one more here. You will observe this is 1 by z cube minus 1 by z raised to 4 will be there. Minus this is 1 upon z cube will be there. and here 9 by z cube will be there. So this z raised to 4 will come, 9z raised to 4 minus 1 z raised to 4, so 8 by z raised to 4, and so on. So that about the required Lorentz series for the third bit, where the region is mod z greater than 2. Mod z is a greater than 2. And the last one now, the region that we have is in between 0 to 1. 0 to mod z minus 1 less than 1. So this is little different now. Our region generally is mod z less than 1 in terms of z, but here the last bit, that d bit, we have 0 less than mod z minus 1 less than 1. Remember, this 0 is of no use. 0 is of no use, and because obviously we cannot get any r for that, so only the second inequality is important. And let we assume that z minus 1 is u. Because of that, you will observe mod u is a less than 1. Now we are going to expand in the power of u, because mod of u is a less than 1. So whenever only z is there, we are expanding in the power of z. But right now it is in z minus 1, the region of convergence given in terms of z minus 1. So we expand in the power of z minus 1. Indirectly, we expand in the power of u. So now our given fz, given function f of z, that will convert in terms of u first. So by 1, if you see the equation 1 that we obtained at the beginning, which is minus 1 upon z minus 1 plus 1 upon z minus 2, here we have to write it in terms of u. So the first term z minus 1 is u, so minus 1 by u plus 1 upon, see, z minus 2 can be written as z minus 1 minus 1, so it will be u minus 1. Now, the first term is already in the power of u because it is u raised to minus 1. Only for the second term, we require this 1 upon 1 minus u. So we should take a minus 1 common from the second. So minus 1 by u minus 1 upon 1 minus u. Now this is like 1 upon 1 minus r, where mod of r is less than 1. And last step then, let me expand in the powers of u now. So the first term remain as it is, minus 1 by u, and the expansion of 1 upon 1 minus u is 1 plus u square plus so on. And that is the end of a question. But don't forget to resubstitute the value of u, because we are given question is in terms of z. So f of z will become minus 1 upon u is z minus 1 minus 1 plus z minus 1 plus z minus 1 bracket square plus so on. And that is the required Lorentz series again, because at least one negative power of z minus 1 appeared there, and this become the required Lorentz series for 0 less than mod z minus 1 less than 1. So that about your assignment 6. Uh, Okay, important thing you should focus, the most important thing you should focus on these two formulas at the beginning that shown 1 upon 1 minus r and 1 upon 1 plus r, provided that mod of r is a less than 1. These formulas will work provided the convergence, there is a convergence, and the convergence occurs only when that mod of r is a less than 1. Based on that, you can easily solve the examples of this Taylor and Lorentz. There is no prerequisite in Taylor and Lorentz, no integration, no derivative, no trigonometric identity, only partial fraction and these two formulae. You can easily solve that. Okay, so that about your assignment 6.